Good day, everyone. I am Kristine and Bayron, a Bachelor of Secondary Education, major in mathematics student. I am here to discuss the comparison test and the limit comparison test. So, first, we are going to talk about the comparison test. B sub n will be our big sequence, and A sub n will be our small sequence. Consider that we're going to consider that big sequence is greater than or equal to the small sequence, and the small sequence is greater than 0. So we're going to use it to perform the comparison test. And of course, we're going to have two cases when performing the comparison test. We have here if the series of big sequence is convergence, then the series of small sequence is convergence also. Take note that we cannot say that if the series of small sequence is convergence, then the series of big sequence is convergent. It is not the case. Now, let's have the second case. If the series of small sequence is divergence, then the series of big sequence is divergence also. And take note once again that we cannot say that the series of big sequence, if the series of big sequence is divergence, then the series of small sequence is divergence also. It is not the case also. Okay? Now, let's proceed to I think it is the steps on on performing comparison test. Let's construct its comparison. Okay? And we have here, we're going to determine the big sequence and the small sequence. Also, we are going to determine the comparison series or the constructed comparison one that we've constructed a while ago, whether it is a convergence or divergence. And lastly, we're going to refer to the two cases of the comparison test. And by this, we can establish that if the big sequence is convergent, then the small sequence is divergence also. And if the small sequence is divergence, then the big sequence is divergence also. So now, since we already having the steps of the comparison test, we're going to try or have some examples. So we have here this. This is the Cuban series. The series of n is equal to 1 infinity 1 over 4 n minus 3 raised to the power of n. So first, we're going to construct its comparison. So in constructing its comparison, we are just going to cancel the bigger value. So in here, the bigger value was, or the biggest value was 4n. So the remaining numbers will be its comparison. So its comparison was series of n is equal to 1 infinity 1 over 3 raised to the power of n. And this 1 over 3 raised to the power of n can be also written as 1 over 3 raised to the power of n. Now, we've already have its comparison. Now, the second one is to determine the big sequence and the small sequence. So, we have here the first sequence was 1 over 4n minus 1 is and 1 over 3 raised to the power of n. Now, take note that if the denominator has a bigger value, the whole value of its fraction was having a small value. So as you can see, this fraction has big denominator. So we can determine that, or we can classify that this is the small sequence and this is the big sequence. So this is the small sequence and this is the big sequence. So take note that big sequence is greater than or equal to our small sequence. Then the third step is to determine the comparison series whether it's convergent or divergence. So our comparison series was the 1 over 3 raised to the power of n. So as you can see, 1 over 3 raised to the power of n is a geometric series. Geometric, please bear with my handwritten because I'm using mouse. Geometric series. So the common ratio is 1 over 3. And if the absolute value of r is less than 1, then we can determine that it is convergence. Okay, it is convergence. So, if we're going to refer into the two cases, now let's have here. If the series of big sequence is convergence. Then, then the series of small sequence is convergence also. So this both series are convergence according to the comparison test or according to the two cases coming from comparison test. Now, we're going to have the example 2. So we have here the series of n is equal to 1 infinity natural log n over n. Now, we're going to simply follow the steps. The first is we're going to construct the comparison test. Oh, the comparison series, it's comparison. Now let's have here, we're just going to cancel out the big values. So we have the n over n, or it simply be 1 over n. Okay? Next is that we're going to determine the big sequence and the small sequence. So the natural log n over n and 1 over n. So we have here, it is simply that they have both the same denominator. So we cannot determine the big sequence and the small sequence using the denominator. But we can use its numerator. Okay? So we have here natural log n is greater than 1. So in this case, the natural log n over n is our big sequence, and 1 over n is our small sequence. So take note, this series was our big sequence, and this series was our small sequence. Now, the third one is that we're going to determine or evaluate its comparison series, whether it is convergence or divergence. So we have here, take note that this 1 over n is a p series. So our p is equal to 1. So if the p is greater than or less than or equal to 1, this is divergence. So now we're going to refer to the two cases of the comparison test. So our small sequence was divergence. Take note that our small sequence was divergent. So in the two cases, if the series of if the series of small sequence is divergence, then the series of big sequence was divergence also. That's it for the example number 2. Now let's have the example number 3. This would be the last example of the comparison test. We have here this, the series of n is equal to 1 infinity 1 over 4 plus the third radical n. So we have here, we're going to construct its comparison. So the biggest value was 4. So we're going to simply crush it out, and the remaining are 1 over 3 radical, the third radical n. Okay. Or we can just simply have it 1 over n raised to the power of 1/3. Okay? So we have here, we can say this one. We can have the or here 1 over n raised to the power of 1/3. Okay. Now we're going to determine the big sequence and the small sequence. The 1 over 4 plus the third radical n and the 1 over n raised to the power of 1/3. So take note that if the big if the denominator has a bigger value, then the value of whole fraction has a small value. So we have here this denominator has, or this fraction has its bigger denominator than the second one, then this is the small sequence and this is the big sequence. Okay? Now, let's have here, we're going to evaluate whether the comparison series was convergence or divergence. So this one is a P series. P series. So we have here the P is the value of P here was 1/3. The value of P here was 1/3. So if P is less than or equal to 1, therefore it is divergence. Okay, so now let's have the two cases. So let's have this big sequence and small sequence. Now, let's refer to the two cases. We have here, if big sequence is divergence, then the small sequence is not divergence. Because in the second case that we had is that it should be if the small sequence is divergence, then the series of big sequence is divergence also. So this is in conclusion. Okay, this is in conclusion. So maybe this maybe can have the limit comparison test. Now we're going to have the limit comparison test. Consider that the small sequence is greater than 0 and the big sequence is greater than 0. So this is our formula in performing the limit comparison test. And if the outcome of it was positive finite number, then we can establish the two cases in the comparison test. So we have here those two cases are we can establish if it is positive finite number. So if the big sequence or the series of big sequence is convergence, then the series of small sequence is convergence also. And we have here the second is if the small sequence or the series of small sequence is divergence, then the series of big sequence is divergence also. So that's it. Now let's have the limit comparison test steps. I think I can call this as steps. So we have here perform the comparison test steps. So yes, we have here, and also we're going to perform the formula, the limit n approaches to infinity, a sub n divided by b sub n. And we have here, we as the result, we can therefore conclude the series using two cases from the comparison test if the outcome is some positive finite number. Okay, now we're going to have the example one. So first, we're going to just construct its comparison series. Number one is that 8 is a bigger value, so we're just going to cancel it out. So we have here n squared over n raised to the power of 5. We can simply have, they have the same n, they have the same value but different exponent. So we can just have 1 over n raised to the power of 3. Okay? And we have here, we're going to compare n squared over n raised to the power of 5 minus 8, and the 1 over n raised to the power of 3. So as you can see, if you're going to determine the big sequence and the small sequence using the denominator, then this will be our small sequence and this will be our big sequence. So now we're going to determine the the we're going to determine the series or the comparison series, whether it is divergence or convergence. So take note that 1 over n raised to the power of 3 was a p series. So the value of p here is 3. And if p is greater than 1, then it is, yes, convergence. Yes. Okay, so now we already perform the comparison steps. So we have here if the big sequence is convergence, then the big sequence is convergence also. Now, after having the steps of comparison test, we are going to undergo the limit comparison test. So here's the limit comparison test. So this is the formula, and to make it easier for you to perform the limit comparison test formula, we are going to just change, we're just going to derive it and have it this one, an times 1 over b sub n. Now, we've have changed the formation of the current formula. So here's the formula that we are going to use. So we simply we simply substitute the small sequence and the big sequence. Okay, take note that our small sequence is n squared over n raised to the power of 5 plus 8. And our big sequence is 1 over n raised to the power of 3. And we're going to, we're just going to perform this, and it comes out as n raised to the power of 3 over 1. And we're just going to n raised to the power of, or n squared times n raised to the power of 3 comes with n raised to the power of 5, and n raised to the power of 5 plus 8 times 1 is n raised to the power of 5 plus 8. So in here, we have this. So they have a this n raised to the power of 5, or n raised to the power of 5 plus 8 is equal to 1. So 1 is a positive finite number. So therefore, we can say that if the we can say that the series of big sequences convergence, then the series of small sequences convergence also. So that's the limit comparison test is. Now, we're going to have the example number 2. We have here this one, this series. So we're just going to simply have this. One is that we're going to construct its comparison. So we simply crash out the big values. So it comes out like this, 1 over n square root of n squared. And take note that the square root of n squared was n. So we can come up with 1 over n. Okay? And if we're going to determine the big sequence and the small sequence of this, is that this is the big sequence and this is the small sequence. So we're going to determine the comparison series, or the comparison series of whether it is divergence or convergence. So this one is, take note that this is a P series. Okay? This one is a P series. 1 over n is a p series. So p is equal to 1. Therefore, it is divergence. Now, we can establish that this one is divergence also if you're going to have or to perform the limit comparison test formula. So this, we have the limit comparison test. This is the formula, and we've changed the structure of this. So we come up this one. Limit n approaches to infinity a sub n times 1 over b sub n. So we just simply substitute the a sub n and the b sub n. Okay? And we have here, we've just, wait for a moment, we've just simplify first this 1 over 1 over n. So this simply have the n over 1 also. So as you can see, 1 times n is equal to 1. And the radical of n squared plus 2 times 1. So we come up with this one. Radical sign 1 plus 2 over 2 squared. So as we can see it in here that it comes out that 1 over the radical sign of 1 plus 0. So it means that it is a positive 1. It comes up with a positive 1. So it is a positive finite number. Okay? So this is 0. Okay. Now, we're just going to have the conclusion. Then, the series of n is equal to 0 infinity 1 over n is divergence. Then, the series of n is equal to 0 infinity 1 over the radical sign of n squared plus 2 is divergence also. So that's it with our video, and hope that you've learned something from this, and thanks for watching. Thank you so much and have a good day. Bye.